A very good morning or a very good evening to sir. Today our group will present our SQQM 3034 Multivariate Calculus group project, and our topic focus on applications partial derivative in physics and also economy. And our group member has only three people, which is Zhen Min, Chua Yun You, and also me myself, Chang Bang. Okay, first I will discuss for our introduction. First thing first, we have our background of study. Multivariate calculus is a branch of calculus that deal with function of more than one variable, while single variable calculus focus on functions with a single independent variable. Multivariate calculus extend this concept to function with multiple independent variables. There are some topics that we have studied in multivariate calculus, which are partial derivative, gradient, multiple integral, line integral, surface integral, and also vector field. And for this project, we actually want to apply our partial derivative in physics and also economy, which is heat transfer and also our utility function. After that, we discuss for our key concept. For our key concept, only focus on partial derivative. Partial derivative, the fundamental concept in multivariable calculus. For the partial derivative, I actually typically did not using the symbol that I show at the df and also dx. For the partial derivative of x with respect to x, where the symbol d indicate a partial derivative. The partial derivative apply when our function is including two or more variable, which is x and y. When I'm using df dx, I will actually act as y as a constant, and we will continue solve our derivative. After that, we go to our concept of second derivative. Second derivative is similar like differentiation. Is only twice differentiated twice. When the first function f of x, we differentiate it, f prime x is actually our first derivative. And for the second derivative, we will take back the first derivative, and we'll simply differentiate one more time. So it will actually become d2f and dx squared. And I will discuss our group project objective. For our objective, we actually want to more understanding how to apply the partial derivative in physics and also in economy. For the physics, we can allow people to analyze how quality like temperature, pressure, and also wave motion change, not just all time, also across space. And for the economy, we can let the company and also chef to maximize to the customer's utility. So the customer will get more satisfactions.
So now, what is the second derivative? The second derivative shows how physical quantity change over time. In a simple word, the second derivative is just the rate of change of the rate of change. Let's take an example, like you walking from a place to another place, the, and we take a derivative from the distance from or your original place to the destination, and we will get the rate of change of the distance in each second. Means that the how the distance change in 1 second, and that is speed. And we take a second derivative onto the speed, we will get the rate of how the speed change in each second, and that is the acceleration. So the second derivative is widely used in formulating the fundamental law, like a simple scenario acceleration or even a complex mathematical model. So The second derivative provides us the ability to predict and analyze the behavior of almost everything in our real world.
The utility function is basically a representation to define individual preference for goods or services beyond the explicit monetary value. In other words, it is a calculation for how much someone desires on the thing, or we could say that it is a study of the satisfaction gained by the customer with the limited explicit monetary value. And the utility function will be shown as above, like u in bracket x1 x2 under xn, which n equals to the total number of the production we select. Next, in order to know how much of effect the certain goods will give towards the utility, we will be calculating the marginal utility function by using the partial derivative, which is fx equals to delta f or delta x, and fy equals to delta f or delta y. We calculate it by only differentiating the x or the y, which is the target variable that we are selecting, but just ignore the other variable inside and make it as constant. And besides this, in the partial derivative, the second derivative also helps us to get the rate of change of this derivative.
So the scenario is that an insulated metal bar with a length of L is initially in a uniform temperature, and it ends suddenly are cooled to a 0 degrees Celsius and are kept at that temperature. So we need to find the temperature at time t and position x. So now we will start with the one-dimensional heat equation, which is the rate of change of the temperature is directly proportional to the second derivative of the temperature along the metal rod. And first, we will assume that the equation of the temperature U equals to the product of the equation x with the variable x and also t with the variable t. And we will take the partial derivative of the equation U with respect to x and also t. And below are the result of the partial derivative of U with respect to t and also the second partial derivative of the equation U with respect to x. And now we will substitute back those two formula into the heat equation. And we will have the equations seems like the equation on the top left. And we will conduct a separable variable which is on our left side is the variable t and on the right side is the variable x. And below that we will equal it to a constant, equal both sides to a positive constant which is the negative p square, so that we will have a general form of the ODE. By solving the both formula from the previous slide, we will have a t equation and an x equation as stated above here. So now we can find our temperature equation, which is the U equals to the x equation multiplied with the t equation, and the result are shown below here. And now we already find our general form equation of our temperature equation. So we will try to find the constant, which is the value of C1, C2, and C3. First, we apply the initial condition into our temperature equation, which is the U equals to 0 when x equals to 0. And we will get the equation like stated above here. And we know that the C1 will not equal to 0, therefore the C2 will be a 0. And now we will get a value of C2 and apply it back to our temperature equation, and we will get a result similar as stated below here. And for the another end of the root, we will applying the x equals to L, which is the end of the root, and U equals to 0, which is the 0 degrees Celsius. And we will get an equation similar like this. And from this equation, we know that the sine PL will equal to 0. So we can write in another form, which is the sine n pi. So now by comparing these two signs, we will get an equation PL equals to m pi, and from that we can get our value P equals to m pi over L. And now we will substituting the P that we will get from the previous side back to our temperature equation U. So we will get an equation like the above. So in a sort of cleaning, we will stat out we will give a simple variable to represent a same constant. So in this case, we will put a Bn. So below here is the general form of our temperature equation. So here is the simple visualization of the heat transfer general equation. The reason why we get a sinus equation is because the 0 degrees Celsius of on the each end of the metal rod. So the temperature T across the metal rod with a length x with a up and down trend, and eventually will decay at exponential rate over time. So the rate of diffusion, which is the alpha, is that when the alpha is large, the heat will diffuse quickly, and the alpha is small, the heat will diffuse slowly. It means that the temperature will take a longer time to become uniform. So this equation is very useful in various of the application, like designing a heat exchanger that maximize the heat transfer, and for that, so it can more have a increasing the saving energy and improving the overall efficiency of the power plant.
In the background of life, we are going on to a food and beverage company. We always do the development, and we are wondering that which type of food actually satisfy our customers. So we'll be using the utility function to make it. So by considering that the other variable are constant, which we are only focusing on two variables, which is quality and the price. So then we will set the function like u in bracket ap equals to a power 0.5 and b power 0.5, as we assume that they both have the same importance. And then we make it to the graph, and then the graph is shown like this. In order to know the effect of each constraints towards the utility, then we calculate this marginal utility, and we know that the marginal utility of A, which is our price, is equals to which is our quality, is equals to 0.5 A power negative 0.5 times B 0.5. While because they are all 0.5, then for the B1 is also 0.5 A, but it is A power 0.5 but B power negative 0.5. On this calculation will implies that how the satisfaction changes when the restaurant increase either the price or quantity of products. Okay, let us take a clear example. We'll substitute 10 and 11 inside, which means that we need to count the rate of change of utility while the price increased from 10 to 11. And we found that the total is negative 0.0073 A 0.5, which means that it shows a negative relationship, meaning that if we increase our price, then the utility we gain is lower. Then we are wondering, is the first derivative really accurate? Therefore, we need to calculate the concavity of the function, which is goes to the second derivative. But why we are calculating this second derivative? As in the methodology, it says that the second derivative is we are calculating the rate of change of the derivative itself. So we're calculating the unmixed second order partial derivative, and we know that they both are the negative value. As you can see, it's negative 0.25 at the front. Therefore, we can conclude that this restaurant shouldn't add in any quality to rise, as any increase of the quality or the price will result in a lower satisfaction of customer.
Last but not least, we finally step to our conclusion. For our conclusion and for our all result that we have shown above before this, we can know that from our discussion, we have clearly know how that our world is surrounding by math. So learning math is very important and is very good for our life because we can actually apply our mathematics in our real life. So the mathematics is actually so beautiful and also so amazing. And For example, even a single calculation of money include mathematics because it have time minus plus and also divide. So I feel like it's very important for our life. Thank you for doctor. Thank you for your patience.